works at BC Cancer Agency, British Columbia Cancer Agency, and he's been working as a research scientist for 8 years there now. And he focuses on data visualization, specifically for cancer research and genome analysis. And his tools that he has developed, Circos, Hive-Plots, and other works that he has done, they've been featured in a lot of scientific journals in Science, Nature, a lot of articles there, but also in popular media, Wired Magazine, New York Times, and whatnot. So I'll let him talk about his craft and help us make our visualizations better. Thanks very much. All right.
Just like verbal communication requires some knowledge of grammar, some knowledge of vocabulary, visual communication requires some knowledge of this kind, but not too much. Can you hear me, actually? I can't tell. Okay. So I'm going to show you what ineffective verbal communication sounds like. Okay. This individual has something called word salad or Wernicke's aphasia, and just listen to him talk. Keep in mind that this person does not know that he is not making sense. Okay, keep that in mind. He thinks his brain is coming up with the right words, but his mouth is not. Okay, I think you get the idea. So that's what it looks like when you draw it. Okay, that's Wernicke's aphasia in visual form. What's going on? It's random, maybe. I don't know. You can't. Okay, you can't. No, it's in the wrong spot. Okay. You can't quite tell what's happening, and maybe my position is wrong. Okay. So you want to avoid these kinds of figures because you can't quite tell this figure from random data. So what makes an effective visualization? It needs to not be confusing, because if it's just information rich, it's confusing, and it can't be gratuitous, because if it's not informative, it doesn't serve a purpose. But it has to be both. It has to have enough information, and it has to be clear so that it's effective. And the idea is to use some ideas of design and to create figures using certain rules that satisfy this. Now, is design subjective or is it objective? Am I going to just tell you my opinions about how things should look? Or are there certain principles, are there certain aesthetics that we all share? I think so. I think one of these is more attractive than the other. And I don't know how many of you have selected Bernadette, and how many of you have selected, I don't know what this is. The point is that this is what I'm trying to convey to you, is you want to be on this side, you don't want to be on that side. And it doesn't really matter where on this side you are, as long as it doesn't offend, because I find this guy a little frightening. So let's look at something called salience, which is standing out, okay? Certain elements, certain visual elements will have salience because your eye will be attracted to it because it is different than the other elements around it. You want to make sure that when you are using elements that are different, they are the ones that are pertinent. You do not make elements stand out that are not important. certain elements like hue and tone will stand out much more than size or even length. I apologize, this is cut off, but that's just a projector. Okay? So that line, if I am counting on you to find that long line in that figure, it's going to be a while before you do, and you may never find it. But if I'm counting on you to find that red dot, you will find it very, very quickly. There's going to be a bunch of rules that I'll cover here, and I hate this slide because I'm tired of telling people not to use 3D. Please don't use 3D. Now, why do you not want to use this? What is wrong with this image? Well, other than the fact that the points are kind of scattered and hard to tell, have you noticed that the axis order here is different than here? These are taken from the literature. I didn't make these up. Okay, I couldn't have made these up if I tried. PC1 is over here and PC2 is over here. The handedness of this coordinate system has changed. How long would it take you to figure that out? You may have never spotted that. A bunch of 2D projections is much better than a bunch of 3D scatter plots. You've seen these splicing diagrams. Okay, splicing is a form of adjacency. It has nothing to do with the position and size of the exons. And yet, tremendous amount of ink has been spent on drawing the exons, making them bold. Not only that, they're different sizes and different positions. And this implies that spacing and size is important. But it's very unlikely that spacing and size is important. What's important is the types of adjacency. So refactor that out. Make everything as uniformly spaced and sized as possible. Align all the elements. Use as few degrees of freedom as possible in your figures. When working with arrows, be very, very careful not to make them too complicated and too fat and too skinny and too stretched. Look at this figure taken from the literature with minor adjustments. There is already an axis of time flow that points up. Fair enough. Time flows up. I get it. Yet all the arrows point up too. That's not necessary. We get the idea that time flows. Here, evolution rate is encoded by arrow thickness. But they know you won't get that, so they put rapid and slow right beside it. Because here, arrow thickness doesn't encode anything. So it's better to show evolution rate as just a line plot and use just lines instead of arrows. Here is a bunch of elements, repeat elements. Well, they all point in the same direction. So really, it's not necessary to use an arrow. Moreover, they're not aligned, and they're all different sizes. And what's happening here? So by actually reducing them to a very simple representation, aligning all the AREs, you can quickly figure out what the pattern is, if there is one. And I've noticed that I've just used, not using color here, I'm just using tone and shape. Very simple. When making grids, 20% opacity is recommended. When you are placing a layer on top of your data, either be something like this or a grid like this, don't make it too dark. And in fact, the denser the data, the darker the grids needs to be, but 20 or 25% is ideal. That's a rule of thumb. And don't put too many grids in, because the more grids you have, the more difficult it is to actually draw your line across. And 10 seems to be about right. And these kinds of things come from studies of visual perception, and people have actually looked at these figures and tried to determine what the ratio is between these lengths, and people have found that with a certain number of grids, they're more accurate. And this is a result of using opacity and layering your information. Here it's very flat. It's really difficult to know what is navigation and what is a grid and what is data. Here it becomes very, very clear. And all I've done is just change the opacity. So when you're using software, make good use of the opacity setting. Legends are something that many people get wrong. One of the things you really want to do is you want to have the order of elements in your legend reflect the order of elements in your plot. This is inconsistent because dark is at the top. Here, dark is at the bottom. Again, we read left to right, up to down. So this is consistent. This is not. If there is no direction to elements, do it so that the dark is at the bottom, because it looks more solid. We prefer stacks of elements with a dark element on the bottom. Unless the one that's most important is dark, for whatever reason you chose the most important to be dark, in which case place it first. Chart junk, Tufte's least favorite term. I wish this term didn't exist, yet it does. Why? Because people publish things like this. That's not necessary. Shimmering textures, gradients, silly things like this. There's a key, I know that's a key, and there's a box around it, and the equal sign, that's unnecessary. I get it. And I don't know, perhaps somebody wanted to draw this and adorn things to make it a little flowery, make it a little sexier, but this isn't. This is that cat on that side. That's this. Okay, this is that dog. And yet it's simpler, it uses less ink. Recall that grid slide. This is from a study by here, where they looked at whether you are good at judging the differences in lengths, whether you're good at judging the differences in areas. This is a really nice study, and they show through actual experiments that we suck at judging relative areas because we use length as proxy. And we even are worse at judging relative volumes because we use length as proxy. Do not count on your readers to judge the difference between areas, particularly when the areas are far apart. Try to bring the lengths close together. This is a great figure. I love this figure. The reason why I love this figure is because there's a very dense data set here that's represented as a contour map with gradient to represent density. But look what happens out here. All of the little outliers are out there. So you can get a sense of where the outliers are. But if I placed all the data, you'd be lost because there would be too much of it. So here's someone who's actually represented the data at different scales. The density here and the outliers here, almost like semantic zooming. This is a really, really, really nice plot. And to emphasize kind of the obliqueness of it, there's a line. It's really good. You've seen these kinds of things where the axis changes on you, and you may not notice it right away. Don't do that. Now, how can I assure you that I haven't done that? I can assure you I haven't done that by only showing you one axis. You will never imagine that I changed the axis because there isn't another one to change. Always have as few elements as possible that can change in the figure. The reader will then know that they're not changing because they only appear once. It sounds very simple, but this happens all the time. Now, what happens when you take all of these concepts and you apply them to a figure? Is it useful? Am I going to make a difference? Yeah, you get stuff like this instead of stuff like this. Okay? This is a different data set, but in fact, this is more complex data set than that, and yet this is unapproachable. And I realize that that's too small for you to read in the back, and if it was made for the screen, I would have made it bigger, but I wanted to contrast the nice colors. They even use lines to help you figure out that there are certain segments that are related. Everything is looking really, really nice. This isn't looking really. There's a whole bunch of things that are wrong with this, but one of them is chart junk. It's overcome by the third dimension, which is unnecessary, not just for actual data, but for representation. So the requirements, I think, for good visual communication is legibility, clarity, and attractiveness. And you have a little handout that I don't read it now. Look at it later, okay? But it's about resolution, and it's about how small can I make things on the page before they're too small. But there's an unfortunate consequence of that, which is that not too small. And because the genome is really big and the features on the genome are really small, you're stuck a little bit. You can't show things to physical size. So that page talks about it a little bit. Read it later. Oh, you've seen this before. What's happening here? What's going on? Why is this painful? Well, it's painful for a bunch of reasons. And many people break the rules. And it's moving. I'm going to move on. So was it moving for you? It was moving for me. There's a whole bunch of things about color that you may not be aware of that I'll cover because it's just the tip of the iceberg, but really the tip of the iceberg is all you need to know. First of all, there's certain colors that are perceived to be brighter than other colors. If you look at HSB, everybody may be familiar with HSB, RGB sliders, HSB sliders. I fixed S and B at 100%. I just changed the hue, and yet the yellow looks brighter than the blue. And so I just changed the hue in this color space, and yet other things have changed. And that's because this color space is a sucky color space for picking colors when you mean to communicate that only one thing is changing. Two things are changing, hue and brightness. So when you make a plot like this and you pick yellow, it overwhelms your attention and you can't focus on the other colors. Moreover, the other colors are so similar that you group them together. And in the end, you just wind up looking at the yellow and it just makes you want to look more, but you don't want to, but you can't help yourself. So you pick other colors. What colors do you pick? Well, these colors have already been selected for you. They're the Brewer palettes. And this is like homework. You Google it and you read about it and you just have this revelation and you go, thank you, I don't have to pick colors anymore. Next time you find yourself picking colors, don't do it. It's already been done by Cynthia Brewer. Select from qualitative palettes. These are great palettes. The colors are calm. Moreover, they don't appear to have no one color is more important than another. That is a key trait. And they don't have an order. Now you think color, whatever, schmuller, right? Your brain can fool you extremely easy. This is the luminance effect. Now, these two colors are the same. And you will say, you're joking. This color looks darker than this color. That's because of the background. Your brain is doing processing you're not aware of, and you can't override that. Try to override it. Go ahead. You can't. You can make it go like this. Okay, but nobody looks at figures like this on the page. Okay, so be aware of the fact that there's stuff going on back here that is happening automatically. And if you're not paying attention, it's going to not help you communicate. Perceived difference is very important. The other problem with HSB is that it's a rainbow, and people have used rainbow color schemes for a long time. And if I fix if I pick two pairs of colors, or I pick a pair of colors, and I make them 60 hue units apart out of 360, and I pick a couple of greens and maybe a couple of blues and this color, the delta H is 60 in each case, and yet these look similar and these look very, very, very different. And so if I'm using a color map that samples uniformly along hue, I get into problems because for the same difference in data, I get similar colors and different colors. That's a problem. So Brewer palettes help here. There are diverging color palettes like a spectral or a two-tone palette. You should never use HSB color palettes. You should really not use spectral, and I'll talk about it why. Use something like pink, yellow, green. This is a colorblind safe color palette, so if any of you are colorblind, you can still tell the two colors apart, and these colors have been selected so that they are uniformly spaced. Now, why does this make any difference? It does. Here's an example from the New York Times, and I know this because I worked with the guy who created this figure. And this is a very unfortunate thing where in medicine they use hue to encode magnitude, right? So here's a brain before and after. The cell phone is on, I get a call, look what's happening to my brain. And the point of the study was that there's this particular area that lights up here. But because the baseline is slightly different, everybody wrote in the entire brain lit up, right? Because it kind of looks like the entire brain lit up. So what did they do on the web? They just added an arrow, and people stopped calling. I'm serious, because they got cued. They were primed that this is the only thing that's different. Here's a reason why you should never use hue. Here's a motivation that you should never forget. Here's a background image, and on top of this background image are two signals, 200% and 150% peaks. And that background is at different positions. And so here you see them, right? It kind of makes sense. And regardless of where the background baseline is, the signals appear to be more or less relatively the same. You'd still say that same thing is happening over here. The image just gets uniformly brighter. But look what happens when I use hue to encode the magnitude. Here, I can't even tell that there's another signal, because if I move a little bit over, the greens look the same, and nothing changes. But as soon as I cross over to another category, like yellow or red, suddenly I get a signal, and I'm fooled into thinking that there's more change than there actually is. Yes, but the environment depends on this. Here's an example, again, from the New York Times. Actually, not from the New York Times, because this figure didn't make it into the New York Times. Here is an example from NASA showing a giant ozone hole in the Arctic, the biggest ever seen. It's pretty important stuff, much more important than the Oscars. But this never made it in the New York Times. Why? Because when it was desaturated, it looked like that. And so in black and white print, it didn't show. So sorry, didn't get the news. Oh, well, the Earth is over. Environmental apocalypse because the wrong encoding was used. I'm not making this up. So what you want to do is you want to encode things like this. If you are ever stuck with this kind of a figure, you have to change the hue and encode it into tone. And now you see this black hole, and maybe that would have made it into the paper. Okay? Real things depend on how you choose to encode your data. The contrast pitfalls, that color example, what's happening there is something called simultaneous contrast. Your brain and your eye, your visual system did not evolve to look at large areas of pure color. A pure color in nature is really hard to make. Chromophores are hard to make, they're expensive, and you don't see these big swaths of really bright red things on top of big swaths. They're tiny little birds that are that bright, and they don't bother you that much. But when it's text, you can't see it because your brain can't figure out whether this is in front of that, it's in the back. Also, when the two colors have the same apparent brightness, which is luminance, this is a perceptual quantity about color. It's how you actually perceive, how brightly you perceive it rather than HSB. When the luminance is the same, you also can't read the text. So when you're picking colors, keep in mind that not only, you're thinking this is too small to read. It's not too small. The contrast is too poor. The black on top of the red can't be told apart because black is dark. Red is also dark, even though its brightness in HSB might be 100, and the black's brightness is 0. So don't do that. Choose a lighter background, as light as possible. But really, is the color here that important? Seriously? You know that this sits on the membrane. You know this. You don't need that. You can use this. All the boxes are the same. And if you want to emphasize that these are somehow different, just do something like this. Again, ask yourself, do I really need color? You don't really need color. This is what happens when communication is redundant. You may not believe it, but perhaps this is a sign that warns you not to hit your head on the sign. Which means what? Which means that if I remove the sign, no problem. So, yeah, you're just kind of just getting it. Oh, that's really weird. Okay. So what happens when you have a figure which makes no sense, and you have to read the legend to get it, and then you no longer need the figure? That's an example like this. What's going on? I don't know what's going on. You have to read the legend, and then you never go back to the figure because you just want it to be over. Okay? When you're making a figure, make sure that the visual form not just complements the text, but it adds to it significantly, worth its weight. So how do you craft a message? You first have to have a message. You need to identify what's your story. What are you going to... I had some sense of what I was going to say when I got up here, some sense. So I need to have that sense. Whenever you open your mouth, you should have some sense, at least by word 2. So let's say you have some raw data. There's the raw data. There's no message here. And what is interpreted? You have no idea. If you do that, you discretize the data. You communicate a sense of scale. You communicate that there's 3 ranges that are important, but not much more than that. There's still several things that could be gleaned from this, that there's more values in the small range, that the big range is closer to the end. If you bin the data like this, you're hiding progressively some information, but you're limiting the number of options the reader has for interpretation. Now there appear to be fewer medium-sized values. And by doing this, you're indicating that that observation is statistically significant, and moreover, that you expect the same number of observations in each bin. In fact, this expected is unnecessary. You know what that dotted line means. You know what that star means. I don't have to say what that star is. So if I were to use some other flowery symbol, like a little heart, that's cute, isn't it? For that, you would think, what is that? You don't know, but the star has a meaning. Use those visual idioms, make use of them. Okay, here's some information about how nucleosomes are spaced. Well, that's great, but do I really need to see all the nucleosomes? If you're talking about spacing, don't show me the structure that many times. Notice how this is much simpler than that. And also there's a hierarchy in this data set. And yet you can't figure that out until you read all the labels, and then you realize that there is uniformly spaced end positions. But it takes quite a while to figure this out. It's a linear search. So try to impose a hierarchy on your representation that is in your data. When you have labels, and you will have labels, make sure that you do not repeat text in the labels because it burdens the reader. And moreover, like I said, when the reader sees things, they expect them to change. And when the reader sees that things don't change, like UCLDN, then they start to think, well, wait, what's the same? What's different? They can't quite figure it out. So factor that out. The only thing that's changing is FMZH. Put that in there and include the number. By aligning it, you make comparison much faster. And if you like, you can color and code it, but you don't have to. This is probably ideal. But look at the alignment. And somebody might say, well, but they're far away from the... You get what's happening. And it's much easier to scan down. Excess ink. So when if I were to draw this figure and I spent more time drawing stuff than information, I have failed. Look at all this. These are some protein alignments. What's different? Let's say, show me the differences, somebody says, and here you are. I'll show you everything. You find the differences. Well, no, you can't do that. You just show the information once and then only show where the differences lie. This might seem fairly trivial, but don't be surprised when you're making a table and you suddenly look down a column and all the values are the same but repeated. And it takes you a while to figure out that they're in fact the same and repeated, and that there isn't a difference hiding somewhere in there. This happens all the time. Okay, so remember that salience and relevance thing. So try to just focus on the red dots that are circled. Okay? These triangles that are circled are competing for attention because your brain is going, okay, red but circled. Oh, but circled. Oh, triangles. And it's really difficult to spread them apart. They're competing for interest. There's something wrong with the encoding here. And what's happening is that there's actually a hierarchy of information that's hidden from you. There is pseudogenes, and there's genes. Okay, so this is the less important stuff, and yet it looks pretty important because it's a star. And the pseudogenes are either processed or not, and they're either transcribed or not. Right? It's a clear hierarchy. And when you do it like this versus like this, you can very quickly, now just look at the solid red dots. That's no problem because the other dots aren't competing as much. Look at the solid black ones. You can see right away where they are. Look at the ones that are solid black, which would be, oh, I hate this figure, which would be the circled triangles, right? How quickly can you find them all? Are you certain you found them all? And in fact, the meaning of the circle is not in the legend. You have to, it's not in the little key, visual key. You have to read the legend. Why? Why can't you just add it in? Should have been added in. This is a beautiful, this is great title, right? This should, in fact, actually, I didn't put in the title, but it actually still works because it's on the cover of Tufte's visual a display visual of quantitative information book. This is a train schedule, okay? And you're saying a train schedule is a table. Why don't I see a table? Well, that's because the representation of a table sucks for searching. If I gave you the train schedule for France and I said, okay, you got to go from Paris to Lyon, and let's see how long you can pause in Dijon here and how long is the voyage going to take you, it would take you forever to figure out the fastest way because you'd have to look at every time and do calculations of time in your head. Here are the train stations. Here's time. Each of these is a train, leaves at 11 at Paris. It's in Dijon at 5:30, half an hour layover. It's in Lyon at 10, right? The slope is the speed, and you can move around here with ease. You could say, I can go here, see my uncle, and then I can be back 5 in the morning, see you for breakfast. Now, what about this? What if I were to say, well, I'm going to put in another train? Because if I wanted to go from Paris to Dijon, and I want to get to Dijon at anytime between 6 and 11, I can't because nothing is arriving there. So if I were to put in another train here, that would be pretty convenient. Would you be able to figure that out from the table? No way. Like, there's no chance you could figure that out in any amount of time. And yet, from this representation, rapid. So representation really matters. I'll talk about network stuff really, really briefly. Okay, you can look it up. So this is the same data. We're using a different layout algorithm. Looks kind of like, is it the same data? I don't know. I have no idea. Maybe I'm lying to you. Maybe it isn't. And the point is, you're not quite sure. And that's a bad sign. This is the same hairball, actually, just rotated. And this is flipped. How long before you believe me? Well, that shouldn't take that long. And yet it does. Here's a really simple network that I laid out manually by hand. Okay, very symmetric. Look at that. Right, can you see the little arrows? Okay. Well, here is one layout, hierarchical layout. Here's another layout of this network. Every information that's useful has been lost. There's no way you can get this out of that. There's no way you can know that this is symmetric. Even these guys are not laid out in the same way, and these guys certainly not either. So you might get that something is going on because they're kind of symmetric, but it would take you a while to figure out what it is. Layout algorithms have no idea what's important to you. No important. Okay? It's like being married to someone, they don't even know what you like to eat. They just give you random stuff. And you say, I don't, that's not what I want. Well, here's something else. That's what network visualization is about. Now, there's a problem with this too. So you say, well, I could, if it's a little saltier, and they bring you something totally different, and just one thing that's different, and they bring you a whole different dish. So here's the network, and I just removed edge E1, and I redrew it from the original data. It looks different. Now, if you didn't know that the only thing I did was remove E1, you wouldn't, how long would it take you to guess that? A while. And here I just removed a node. It would probably take you a little less time to figure out a node was gone. But that's a bad thing. So imagine a scatter plot where I remove one data point and all the other data points just get more comfortable and move around. That would be really sad and disconcerting, and you wouldn't want that scatter plot to be shown to people because there's something wrong with it. That's what network visualization is like. Let's look at this figure. There's no chance of you finding any patterns in this figure whatsoever. Zero. Right? And you would never be comfortable saying, I've looked at it long enough and I know there is no patterns. Because you'd think, well, I think I missed something. And I wouldn't be surprised. You would have missed something. There's a lot of stuff that's going on here. And it breaks a ton of rules. Let's look at some of the rules that it breaks. Okay. First of all, blue and blue don't blend to make purple and yellow and this color with any other color at the same time. So when you have Venn diagrams, use intuitive color blending using blend modes. Illustrator, Photoshop, blend modes, multiply, linear burn, color burn. That drop-down box combines colors not in a linear way, RGB plus this, but in some other way, maybe more contrast. It multiplies the RGB values. You use that. Okay, well, here are the points. You kind of get what's going on. There's some different observations here associated with different pathways. And they put them all here because they think that it'll be really nice to fill them, but they know you can't count, so they put the numbers in there just in case. But they say, well, we're not going to use the same yellow. We'll use orange instead of yellow because yellow doesn't show up on this yellow. So you make a bad choice, and now you're stuck with that bad choice. So instead of undoing that bad choice, you make another bad. You've been there before. And next thing you know, you're somewhere where you don't want to be, and it's late, and you can't get home. So where are the patterns? How would you fix this? How would you fix this figure? There's too much information here all at once. You want to break it up into little chunks, like chewing and biting and chewing and repeating until you've eaten the whole thing. The first thing is to communicate to people that, okay, well, there's a couple of categories, and there is a couple of groups, and use this kind of maybe intuitive way of saying that the groups overlap. And just give people numbers. Give people a rough idea of all pathways, all observations. So in other words, I don't really care about the differences in color here. This gives people familiar with the idea and the way you're splicing the data up, even though you haven't shown them all the information. But you have included this. Well, if I apply a filter, right? Everyone knows chi-squared, it's a filter, you're kind of removing data. Something going on, there's a certain proportion of values that is changing. And then you follow up from an introduction to, okay, well, here are the details for every pathway. Here's the number of observations. Here's the grid. Notice that I only really need to put 5 here. I don't need to tell you that that's 10 and that's 15. You know that. And the reason why I don't is because I don't want to put numbers here because you may not trust me to not change the axis on you and suddenly go 2, 4, 6. And look, you can see what's happening, that the values that have failed the chi-squared filter all seem to come from the gray area, right? Gray is gone, the gray is gone, the gray is gone, but the blues seem to be intact. The camp GC is gone. Could you tell that from here? There's no chance that you could tell that. By splitting rich information up into chunks, a very useful thing to do. How much time do I have? Oh, good. So here's a whole bunch of information. And there's a couple of problems here. Can somebody tell me maybe, what is problematic with it? What causes you concern with this figure? Nothing. Are your eyes open? There's no trace falling through the spots, for example. Yeah. The scales are different. Oh, 6. And that took a while. Okay. Yeah, 2. Sorry? The titles are all over the bloody place. What's going on? This is closer to this. This is what? Like, yeah, it is. But why? Why? Right? If somebody comes to you and says, and you say this is ugly, then they expect you to say, and this is why, and this is how we fix it. Okay? The labels are terrible. Too many things are varying, and these extremely stout lines are separating the data. And they're very heavy and unnecessary. So you want to lighten things up. You align things and you compartmentalize things using negative space. Do people know what negative space is? It's where you don't put stuff. Like that gutter here. That's negative space. There's just a little bit of it, and that's enough to create visual separation. Labels are aligned. That's pretty good. And the axis is shown only once here. I think that this is a different data set here than here. I think that's why the axis is different. But what I've done here with the line is to give you a sense of what the baseline is. I largely made it up because they didn't give you what the baseline is. So I tried to get into the heads of the authors. And I said, well, maybe you're going to be interested in certain comparisons. Maybe you're going to be interested in the average. Maybe. Otherwise, what's the point of showing me all this data if I can't compare it? Emphasize that with a little red line or a dotted line or something like that. If the point is to contrast and compare, make maybe even the data points lighter. Make them sit behind and lower their opacity so that they don't figure so prominently. Don't worry, your reader will see them. Let's look at this final example of how to fix this. There's nothing particularly wrong with this figure, but it's kind of all over the place and it's very jittery. The layout is poor. These call-out lines are all at different angles, and the person had to make them at different angles because these areas are in different place, and these are all boxes, and they need to be put somewhere nearby. And is that really true? Is it somehow possible to place these boxes near where they belong without using lines to connect them? I think there is. I have never found out why these areas are different sizes and shapes. It doesn't say anything in the paper, so I'm going to assume that it doesn't matter. Okay, so we'll start with the outline. And here's a point. When you know you're talking to people with an LCD projector and you don't know about the quality, be aware that it can wash out light colors. Actually, this projector is pretty good. I can tell the difference. I can even see that. I don't know whether you can, but I think I can persuade myself that I can see it. Some projectors, you may not be able to see anything here until you get to RGB 230 or 225. So avoid the use of very light colors. So here's the outline, and here are the points from which I will sample my data. And now I want to put my pie charts, but I will make a contract with myself. I will only put pie charts on a grid. I will only put them on those circles. And then I look and I say, maybe I need some more circles, so I'm going to double up. Okay? I'm going to make a grid for myself. That's the only place where the circles can go, and here they go. Suddenly, there doesn't seem to be any confusion as to where they belong to. They're close enough to one another to not confuse them. There's no chance of you confusing this with that, and this goes here, and this goes here. There is a couple of issues, and for that, I've removed the grid, and for that, I have to use a little line, because I just can't get them in there, and I don't want to break that grid contract with myself. But these lines are both oriented at 45 degrees. And that's very important, because it means that fewer things are changing than if I were to place them at any odd angle. You, again, want to change as few things as possible for the reader to give them visual comfort, that, you know, it's nice and it's clutter-free. I know we're not all OCD, but assume like your reader is easily persuaded to be OCD. And certainly when it comes down to interpretation, they're going to become anxious when they start to lose comfort in your ability to guide them through the forest of information. Okay? And, okay, here's the legend. And so you could argue that in some way this is easier to make, because I don't have to decide where those circles go. It's decided for me. And that's like picking the brewer palettes. The colors are decided for you. You don't have to decide anymore. Isn't that comforting to know that you can focus on other things, or maybe have more time to sleep? Typeface selection, which I didn't talk about. Also, don't feel like you need to select typefaces. Helvetica, it's the only choice. And I don't think that it's necessarily the best choice, but it is an excellent choice, and probably better than 99% of the things that fall in the drop-down menu on your operating system. Certainly some of them should not be there. Just pick Helvetica. And then when you realize that there are other good typefaces out there, go and seek them out. So go and buy 4 weights of Helvetica. It's going to cost you $80 perhaps, maybe split it with a friend, you know, and enjoy it. And you can establish a type hierarchy by just changing the type weight, and you don't necessarily have to change the type size. It's really nice when the size of type isn't changing, when it's consistent. Okay, so do you know what, are you saying something? That's really important. Keep in mind that when a reader is expecting a message, when a reader reads text, they expect not Wernicke's aphasia. You don't want that. You don't want just a bunch of symbols. You saw those little shapes, right? The little sickles, and you don't want that. And is it salient? Is the right thing standing out? Or is the flash the noise? And have I used the simplest representation? Can it be further simplified? Can I remove elements from the figure without impacting the message? Remember, the reader will assume that everything you have shown is important, because that's the best assumption to make, and that everything you have not shown is irrelevant. And you do not want them to realize that that assumption is wrong, that something is missing or something is extra. And the relevant hierarchies is really important when you're making a visual key, a legend, because if you can craft a legend in the form of a table, you very quickly let the reader know that there's an organization behind the data that they can take comfort in and solace in and go there when they feel confused. Okay? Thank you for your attention, and I have 4 minutes for some questions. Yeah?
So just a quick note. I think
Yeah.
Do you have some example that
I do. Yeah, I can show you. Well, they're very similar to what I have already shown you, but I will. This. Okay. Okay. There's going to be some repetition here. Okay. I'm trying to hit it really, really fast. Okay. Well, here's more examples of the same data shown in different ways. So this is a bad idea. This is from the paper. So something is not. And which one do you pick? I don't know. It depends. Whether you have millions of nodes, you use this open-ORed scheme, which is excellent for a very large number of nodes. But it really shows you things it compacts all of the clusters down to a single point. This thing takes forever, and this stuff, well, who knows? And there's so many parameters in each one of them. Okay, right? We got that. You rotate it, and it looks different. Well, here's different layout of that same network. All of them, they're useless. And this is what happens when you change it in. I showed it to you in the Sugiyama one, and here's what happens when you change it with the Spring embedded. It's also useless. So here's a start from a paper that compared E. coli to the Linux kernel, where it said, okay, well, E. coli has genes, the Linux kernel has functions, functions call functions, gene regulate genes. That's kind of similar. Okay, let's go with it. So the master regulator are genes that regulate other genes but are not regulated by genes themselves, functions that call functions but aren't called themselves. Middle manager is the guy who gets the orders but also sends the orders, and the workhorse is the guy who gets the orders, right? That's like us. And you see that, okay, well, they're on a line, so that's not bad. You can see that there's more workhorses in E. coli than Linux, and Linux is middle heavy and so on. And all of these lines are just there for what? They don't tell you anything because the nodes aren't ordered along these lines in any way. They're just dumped there. But if you were to change the rules a little bit, things might be better. If you were to put the nodes on straight lines and put the regulators on this axis and the managers on this one and the workhorses on this one and position them based on their connectivity, suddenly you're capturing useful network properties and putting them down in a quantitative way, like a scatter plot. In fact, this is, do people know what a parallel coordinate plot is? Right, a bunch of lines, a bunch of y-axes parallel to one another, and it's a multi-dimensional point, and the lines connect all the coordinates of the point. It's kind of like that if these were parallel, but they're not. They're like this. Okay, well, this tells you a lot. So here's that original layout that I did manually and tediously in Hiveplot. Oh, look, it's symmetric. That's kind of cool. And also, if you remove one of the edges in the layout, well, guess what? Only this moves. And any node that is affected by it, whose properties are affected by it. So because this node suddenly loses an edge, its connectivity drops. So that node drops down by 1. And you can assess quickly the differences. I know this looks a little complicated, and for this purpose, I mean, I'm pulling up a thing from a paper. It looks really foreign. But so does a language that you don't know, and yet there is hope of you learning it, and one day you can master it. And this isn't a foreign language. This is just slightly new. It's like a phrase. And you can get an idea of it very quickly. And the nice thing about it is that, like those colors which are perceptually uniform, this is kind of perceptually uniform in that the differences in appearance are commensurate with the differences in the underlying data set. Okay? Everything doesn't just change just because you remove the node. Okay, so here's the E. coli regulatory network. Favorite, whatever hairball it is, I don't know. Now, what can you tell me about this? Well, you know, here I am. I'm talking about systems biology. Please help me. I can't figure it out. Come and be my student. Help me. You don't know what's going on. And do you stand a hope of finding out what's going on? What are the patterns? I've drawn some labels, and I might talk about this gene. But are you sure that I have drawn the label to the right gene? If I said this is the most connected manager, do you believe me? No. Because it might be hiding elsewhere, maybe this guy. So I'm going to skip right ahead to this. So if you draw in a hive plot where this is the regulators, these are the managers, and this is the workhorses, Well, where's the most connected manager? He's out here. Right? He has to be there because that's the manager axis, and they get put on that axis by their connectivity. So the guy at the end is the most connected one. This is the most connected regulator. And look, I'm going to turn the labels on. Oh, it's NSRR, okay, but all the lines that come out of it are red, repressor. So the top level boss of E. coli has a repressing effect on all the genes that it connects to. Would you have figured that out from this? Well, there are a bunch of red lines from it, okay, but are you sure that there aren't other lines from it? And how about, does it connect to the managers or the workhorses? In what proportion? Can you tell? No. But here, you can tell. You can tell that, actually this you can't get from that layout, no matter how hard to try, is the top boss is not connected to the two top managers. So those managers are insulated from the top boss. Now this may have a biological reason or it may not, but it's certainly a system that seems to be set on negative feedback. You don't want E. coli positively feedbacking itself for no reason whatsoever. It'll just explode. And also the connections between the top managers also seem to be repressive. I realize that the lines are a little too thin for the display. They seem to be repressive. There's no green lines here. You can't get that from that hairball. You can get this from here. Moreover, it nicely accommodates annotations, for example, like the fraction of colors of lines coming into a particular area. And because everything is quantitative, like a scatter plot on an axis, things fall into a pattern. And I'm not expecting you to take the layout algorithm for granted because you know what the layout algorithm is. I just explained it to you, and we've agreed that it's useful. And if it's not useful, you can select some other quantity that's meaningful to you, some other network quantity, connectivity, betweenness, whatever. So essentially, okay, I'll stop there. So essentially what it is it's making a scatter plot in a way, except things are connected based on the properties of the network that are meaningful to you. And it solves a bunch of problems that the hairballs don't address or solve accidentally. Okay, so that's a quick.
So I'm missing something. It seems that there are four axes, but there are...
Okay, right. So in this case, what happens is managers can talk to each other because they're defined as genes that regulate other genes but are also regulated by others. So where do you put the connections between managers? If that axis was collapsed, the link would look like that. So by cloning the axis, you see the conversation in between those nodes. That's why it's spread apart. And yeah, there is a choice of symmetry as to which direction you come in, but you can kind of use some convention. And if by definition, there is no connectivity between workhorses, right? And by definition, there's no connectivity between regulators. Just because it's a tripartite network. Those are the ones that only have out edges. Yeah?
So let me first start with a comment that is a great talk, and I wish more of my colleagues were here. Maybe there was we would have a few advice whenever we are trying to publish something. So I have a couple of questions. Well, first one is about the policies that journals have regarding the publications. If you look into how the papers are accepted and camera-ready versions are being prepared, basically there is no supervision for the journal.
Yeah, that's right.
Regarding the figures preparation.
Yes.
And tables preparation.
Yes.
Graphic. I mean, sometimes I read the paper and I see table that is completely messed. And of course, figures is a whole another story.
Yeah.
So I wonder, do you think there's any way to change this without actually, as a faculty, I don't have much, the skills like yours. So I'm expected publishing fee to the publisher.
Yeah.
They will take care at least partially of reviewing this.
Yeah, you would hope, but they don't. So what can you do? You can take it upon yourself to, when you are asked to referee, look at ugly figures and say this figure needs to be changed and criticize the figure in the same way as you criticize text. If I were to come up here and Wernicke aphasia you for 5 minutes, somebody would stop me. Somebody would. I know it. Maybe it would take a minute before you thought maybe it's a joke. But I could put ugly figures for an hour and nobody would stop me. Because you say, well, it's terrible, but we know it's going to be bad. So we somehow allowed that to happen. And we all allowed each other's figures to get ugly because we don't criticize them. I mean, you don't want to be rude, but you want to be emphatic. Say, look, that doesn't make sense. Can you please make this change? And look at this paper because this is where it does, this is the paper that does it right. So, you know, stand up to the standards that you wish to set. 2, yeah, journal make unreasonable expectations. A lot of times, they don't want any work. They ask you, for example, to send them CMYK. And for those who don't know, so CMYK is a color space, cyan, yellow, magenta, black. Okay, so it's a device-dependent color. It's the amount of ink that a printer puts down on the page to reproduce a color. What printer? Well, I don't know. Depends on what print house they're using. You'd think the print house knows how to make that conversion. I don't. Now, I could use swap. I could use a certain standard. But that's like just using sRGB. It makes no sense for me to give them CMYK. It depends. They're taking care of it. So they do burden the author with too much, I think. In that case, and they don't give enough. So what we need is a set of guidelines and standards. Some of them help you and say, okay, no more than a 1/4 point line thickness and 6-point font in Helvetica, but that doesn't help you. So it comes down to the referee, it comes down to the editor, and it's sad. But you know, maybe that's what you need to do, is you need to draft some kind of a standard and say, look, I'm going to buy into this standard, and if the journal buys into this standard, you know, you don't necessarily need to get paid for it, but they say, oh, we adopt the your name here standard. And more people will maybe likely read them. Maybe people want to adopt that standard because they want to say, yes, we're also environmentally responsible. That, you know, so write a manifesto. That.
I would ask one more technical, very technical question. Do you think that color management is really important for the scientific publishing? Like,
no, you just pick color brewer palettes and then you don't need to worry about it. So color management is not unless, so what does color management mean? It means, let's say you have a device in the lab that collects an image, let's say some kind of a gel scanner. I don't know, I'm not a lab person, I can't drink coffee there, so I don't go in there. But let's say there is, and there are images, like I know there's equipment that have cameras attached to them. Well, that camera sees color, that camera sees light, and it responds to that light by recording some RGB value. And then that camera passes that RGB value over to some other program, which then passes that over to a printer, which then prints the color out. And then you look at the color, and you have to ask yourself, is that the same color that I would see if I were to look at the thing that was being photographed? How can I track the property of the device, the property of the sensor, the input sensor, the property of the ink, so that that color is as consistent as possible? So that's color management, okay? And is that important? If you want to print in the journal an image of the exact color that you saw, that's probably not that important. You don't want to fudge the image locally. You don't want to start adjusting local contrast on gels. You probably also don't want to adjust global contrast in a way that will make the gel look terrible or too good. So I think that their color management is not that useful, but you do want a calibrated screen, probably. So when you look at your screen tonight and you look at white, okay, white, depending on that thing up there, that might be blue. That might be bluish. That might be yellowish. And you might be fooled. Remember that luminance effect that I showed you, where you had the same color that looked different based on the background? Well, that color will be affected by that color. Your eye will automatically try to correct. And if you're trying to select something of a cooler color, and your screen is already cool, you might be freezing things too much. So in that way, having a calibrated monitor that has a good white, a neutral white, is useful for everyone. But I think you can't worry about it, because if they just send me swap, send me CMYK, you just broke the rule. So don't worry about it. Just pick brewer palettes and relax. Yeah. So that's good.
There's a question. We'll do one more question, and then I guess you guys can come out outside and during reception.
Yeah.
There was a reference you mentioned that I think you must have discussed in the launch with the students. Some kind of was it? A book that describes some of these rules. Could you share
Tufte?
with us?
Tufte's book?
Yes.
Okay. So it's I have it. I'm going to show you the cover for that book. Okay, it's that book. Okay, and it has that train thing on the cover, that train schedule. Tufte is someone who tries to champion this, and he has put into words many of the things I've said, all of the things I've said plus more, and he has several books where he makes fun of PowerPoint. It's quite amusing. And you should get this book. It's not very expensive, but it's very, very useful. And if you were to only buy 2 books, you'd buy this one, and you'd buy, if you are interested in type, and you are interested in choosing the right type, and learning more about some of the technical aspects of type, is Bringhurst's Elements of Typographical Style. It's a very good and inexpensive book. Both will probably cost you only $50 together. Excellent, 2 excellent books. And many of the things that, now I showed you examples, bad examples from the literature. Those abound. He shows you bad examples too, some really atrocious ones. But he also shows you really good examples and points out what makes them very good. And I think this is the best figure of the book, because if you think about the fact that now I'm just using straight lines, I'm not even using any other shapes but straight lines. For a more effective visualization, where I'm showing you the data, but I'm not showing to you in the raw form. Think about the fact that you can choose a representation sometimes that just makes a world of difference of how it's interpreted. That's the book.